This is the review of real numbers and their properties, the prerequisite chapter for Algebra 3, Section 1. Okay, first of all, a review of the real number system. Real numbers can describe quantities in everyday life, age, miles per gallon, and population. Some of the numbers that you can find in the real number system are here on the screen in front of you. Notice it includes negatives, positives, zeros, fractions, decimals, even numbers like square roots and pi. All of those are in the real number system. The real number system is made up of smaller groups of numbers. The first group that we talk about is the set of natural numbers. When you think of natural numbers, think of the numbers that you start with as a child. You don't usually start counting with 0. You start counting with 1, 2, 3, 4. Those are the natural numbers. When you throw 0 in, right here, you now have the set of whole numbers. Nothing's changed except you've added in 0. Then we throw in negatives. Now we still don't have fractions yet or decimals, but when we put the negatives in there, that is called the set of integers. The next subset of the real number system would be rational numbers. And now what we're going to add into the mix are numbers that can be written as the ratio or the fraction made up of two integers, as long as the denominator is not 0. Some examples: 1/3, 1/8, 1/25 or 1/11, all of those are rational. Now you'll notice that the decimal representation of all of these is either a repeating decimal or is a terminating decimal. So rational numbers, the decimal equivalents must be repeating or terminating. A real number that cannot be written as the ratio of two integers is called irrational, and they have decimal equivalents that are non-repeating. They don't have a pattern and they go on forever. Any square root that doesn't come out terminating will be irrational, like the square root of 2, the square root of 3, the square root of 11. Pi is also an irrational number. Here's a chart that shows how everything kind of works together to form the real number system. We start at the bottom with the natural numbers and 0, and they're going to come together and make whole numbers. When you combine the whole numbers with the negative integers, you have the integer system. When you combine that with the non-integer fractions like 1/2 and 1/3, both positive and negative, we get the rational numbers. And when we combine those with irrational, it makes the overall real number system. Okay, here's our first example. And we need to determine which numbers in the set belong to the natural number system, the whole numbers, the integers, the rational numbers, and the irrational numbers. So why don't you pause this playback for right now and see if you can figure out which numbers belong in which of these systems. And you will use most of these numbers, or several of them anyway, more than one time. Okay, the answer. Natural numbers would only be 7. Remember, natural numbers do not include zeros, negatives, or fractions. B, the whole numbers would be 0 and 7. Integers, we're going to include the negatives now, -13, -1, 0, and 7. The rationals, all of them except the square roots and pi are going to be our rational numbers. And then finally, the irrational will be negative square root of 5, square root of 2, and pi. Now you can represent real numbers graphically on the number line. You've done this since elementary school. When you draw a point on the number line, that's called plotting the point. 0 is called the origin, and to the right of 0 is the positive direction. To the left of 0 is your negative direction. You're going to see the term non-negative or maybe even non-positive in this book. The reason they use these terms is when they want to refer to either the negatives or the positives, but they want to include 0. 0 is not considered to be either negative or positive. So if you only say positive numbers, then you're excluding 0. By the same token, if you say negative, you're excluding 0. So in order to include 0, they say non-negative, which means 0 and the positives. Non-positive would be 0 and the negatives. When we plot numbers on a number line, there's a one-to-one correspondence between the real number and the point. What that means is that every number corresponds to exactly one point, and every point matches up with exactly one number. Okay, here's another example. I'm going to graph some points on the number line. You should pause here and try this for yourself, and then I will give you the answers. Okay, the answers. And again, these are all on one graph just to save some space. A, -7/4 is between -1 and -2, as is D, -1.8. They're very close. B, 2.3 is off to the right, and then you see where C is. If you have difficulty graphing the -7/4 and the 2/3, I suggest that you change them to a decimal for the purpose of graphing and getting a good idea of where they lie on the number line. Okay, an important property of real numbers is that they are ordered. There's a definition of order on the number line, and essentially what it tells us is that if you have two real numbers and you subtract them and you get a positive answer, then the first number was greater than the second. However, if you subtract them and get a negative answer, then the first one was less than the second. Our symbols for inequalities are given there in the last sentence of that definition. We have the less than symbol, the greater than symbol, less than or equal to, and greater than or equal to. Those four represent our inequality symbols. You also could consider the symbol not equal to as an inequality, although we don't use that very much. Geometrically speaking, on a number line, a number that is to the left of another will be the smaller number. So in the example, A is less than B because A lies to the left of B. Another example, you need to place the appropriate inequality symbol, either less than or greater than, between real numbers. Pause this recording for a moment, give it a try, and then turn it back on and check your answers. Okay, letter A, we can see that -3 is less than 0. On B, -2 is greater than -4. If you're wondering why, you need to remember that the number farther to the left on the number line is the smaller number. Negatives can be very tricky, so be careful. C, 1/4 is less than 1/3. Again, converting these to decimal can be a big help. Sometimes it's really hard to picture where fractions lie in relationship to each other. And D, two things here. We have the negatives again, which is tricky because it's almost like it works backwards from the positives, and then you've got fractions. So again, I would change the fractions to decimals if you struggle with fractions, and I would picture them on the number line. -1/5 is greater than -1/2 because -1/2 is further to the left. Okay, a little word about ordering. It says that inequalities can describe subsets of real numbers called intervals. In the bounded intervals below, the real numbers A and B are the endpoints of each interval. The endpoints of a closed interval are included in the interval, whereas the endpoints of an open interval are not included. Okay, a few things there. First of all, that word bounded. The word bounded means that the interval has endpoints. It has two boundaries. So all of these have a start and a finish. Little bit of a new notation here. For a long time we've used the greater than and less than. Well, now we're going to learn a new type of notation for it, and you need to be ready to start using that and switching over to that. Okay, let's look at this chart here. Notice in all of these, A is the lower point, B is the higher point. The first notation, you have A comma B in a set of brackets. This is called a closed interval. The reason it is closed is it has a definite start. It starts exactly on A, and a definite end. It stops exactly on B. Using inequality symbols, we would write this as A is less than or equal to X, which is less than or equal to B. Notice the graph. We're using the same notation on A and B. We're using those brackets on the graph. What you've used up until this point have been open and closed circles to indicate whether the endpoints were included or not. Now you're going to use brackets and parentheses. Okay, our second notation is AB in parentheses. This is an open interval because even though it has endpoints A and B, it doesn't exactly begin on A. It begins right after A. Well, what is the number right after A? We don't know. What is the number? Let's give it a real name. What if it's 2? Well, what is the number right after 2? There's no way to write that. It's not 2.1, it's not 2.01, it's not 2.000001. Because we don't have a definite starting point, we just know it starts right after 2 or right after A and it ends right after B, right before B, then it's going to be an open interval because it does not have definite endpoints. Inequalities, we would use the less than symbols. We would not use the equal under it. And notice on the graph, you've got the parentheses for A and B, not the brackets. Okay, the next one is one where we have a definite beginning at A, but not a definite end. It ends right before you get to B. So this is still open. It's only going to be closed when both endpoints are definite. Notice the inequality. The A is less than or equal to X, but X is only less than B. And then notice the graph. The last one is the same idea, but this time A has the parenthesis, B has the bracket. A is not a definite starting point, B is a definite ending point. All right, some more symbols we have. We have infinity and negative infinity, and they do not represent real numbers. There is no number infinity. You cannot go to infinity or beyond, so I'm sorry if that disillusions you. They are simply convenient symbols that we use to describe the unboundedness of an interval. In other words, an interval that does not have either a starting point or a stopping point or both. And you'll see what we mean here. First of all, the first notation is from A to infinity. A has the bracket that tells us it starts exactly on A. Infinity never ever has a bracket by it. It always has a parenthesis because it's not a number and it cannot be reached. So you can't put the bracket there. It's got to be the open parenthesis. By the way, all of these are going to be open intervals. The inequality for this would be X is greater than or equal to A, and you see the symbol there. We have a starting point at A, and then the line goes to the right forever. The second one, A to infinity, both parentheses there. That just tells us that X is greater than A. There is no equal. The next one, we have negative infinity to B. This is the same idea going in the opposite direction. X is less than or equal to B. Then we have the same thing but no bracket. And finally, when you want to express the entire line using interval notation, you're going to go from negative infinity to positive infinity. And again, notice infinity and negative infinity will never have the brackets. They will always have the parentheses. And another example. You want to write the inequality that represents the given interval. Okay, pause this recording and try this problem, then resume and check your answers. Okay, the answers. The inequality C is less than or equal to 2 can represent the statement C is at most 2. If you have at most $5, that means you have $5 or less. So less than or equal to 2. And then secondly, the inequality negative 3 is less than X, which is less than or equal to 5, represents all X in the interval negative 3 to 5. Notice that the negative 3 is the parentheses by it because it does not have an equal under the inequality. 5 has the bracket because it does. And this is out of